So I hope I'll be able to focus my mind on what I'm supposed to tell you rather than whether the recordings function or any of the other logistics. But my talk is going to be sort of a complement in some sense to what David gave us just before the break. So David was arguing that quantum gravity, at least in some of its versions, in the low energy regime, we actually have a reasonably good, reasonably well-defined and developed theory which is empirically well supported. I'm gonna not talk about the low energy regime here, but really looking more to attempts to formulate a quantum theory of gravity which is ultraviolet complete, which has maybe some hope of being a fundamental theory. It would certainly be a fundamental theory relative to low energy quantum gravity, to the standard model of particle physics perhaps, to GR, and so on and so forth. And as you all know, there is a challenge of getting empirical input for that. We have plenty of theoretical input, plenty of ideas. We can use principles, we can use techniques, we can use approaches to formulating physical theories that we've used successfully elsewhere. But the question, of course, is whether these principles, techniques, theories, etc., will actually continue to give us the correct results in those regimes in which we haven't tested the physics. And that's exactly why, at the end of the day, we will need some form of empirical confirmation. We will want that. So how are we going to get that? So that's the point I've just made. Theories of quantum gravity, not in the general sense that David understood them, but in a more, how should I say, in a more ambitious way of trying to have a UV complete theory or so. That's really hard to have a test, sort of empirical input for any such theory. Now, it's at least the case that it's difficult to come by with an empirical test, as it seems as if these theories describe phenomena at the high energy scale far removed from what is accessible, say, by particle accelerators or other ways of testing high energy physics. Now, of course, ostensibly here is supposed to be understood as a qualifier for the following two reasons. Even as theories of high energy physics, they may well have testable low energy signatures. So for instance, if we have string theory or some other theory of quantum gravity, it may have some consequence, supersymmetric particles or what have you, something else, that might be testable in a regime which is much of lower energy. Perhaps we'll find signatures of quantum gravity in cosmological data, etc., etc. In a way, then, more generally you say, that this is why I say two related points. I'm not sure they're really separate points, but more generally speaking, if theories of quantum gravity are fundamental theories, then they should have some universal scope, or at least more universal scope than the theories which we have so far. And so one would expect that they may show themselves in possibly many ways, given the wide scope of these theories. Okay, now, if we're really interested in, let's say, high energy quantum gravity, or not so low energy quantum gravity, then it's very natural and straightforward to look to two places, namely to cosmology and to astrophysics. Cosmology in particular, the very, very early universe, sort of pre-inflationary stage of the universe where it's supposed to be the quantum gravitational regime, and to astrophysics, and in particular to black holes, of course. And so one direction in which physicists look for any guidance in their search for a theory of quantum gravity is black hole physics. I'm going to sort of bracket cosmology, maybe as the computer doesn't agree with me that I bracket cosmology for today. We'll hear more about cosmology later in the week. I'm going to focus more on astrophysics in the sense of looking at black hole physics. And in fact, maybe, black hole physics, it's at least considered as such by many physicists, might be something like a Rosetta Stone, giving us a handle to translate between quantum physics and relativistic physics, where both of these are ineliminably part of what we're trying to find. And so maybe we'll see something in there which allows us to translate back and forth. I'm not sure whether the analogy with the Rosetta Stone is really quite complete, but it's something in this direction. Now, David is going to talk about black hole thermodynamics in the second talk. So I'm not going to give you a lot of details about it, but just very briefly, the assumption here is that the hypothesis, the working hypothesis is that black holes are thermodynamic objects. That is, they have temperature, they have thermodynamic properties. They have temperatures, they have entropies, they radiate through what's become known as Hawking radiation. In particular, here's the way to compute the black hole entropy. It's the entropy which has become known as the Bekenstein-Hawking entropy, to calculate the entropy of black holes, where A is the area of the horizon and LP the Planck length. So you can see that the entropy grows with the area of the horizon. Hawking in 1975 did a famous and often cited calculation of a quantum field theoretical vacuum state in a thermal state, and he found that in the presence of a black hole we have such a state. And in fact, we find that the radiation which arrives at the infinity, the asymptotic observer, with a temperature which goes with 1 over the mass of the black hole. That was the famous finding. I'm not going to go into more details. I'll take this here as a given. In fact, so in short, the Hawking radiation is black body radiation of a black hole at the temperature as seen as infinity, inversely proportional to the hole's mass. Okay, that's black hole thermodynamics on one slide, if you permit. Now, the question then for us, physicists say, or philosophers of physics who are interested in a full theory of quantum gravity, the question is whether we can use any of this as an empirical ground on which maybe to confirm theories of quantum gravity. And here's a problem with this. Black hole thermodynamics is a theory, if you want, which is theoretically extremely well motivated. It extends tested, established physics in a very straightforward, plausible, consistent way. But it's really hard to actually empirically confirm that black holes are thermodynamic objects. It would be nice if we could detect the radiation of a black hole. We could have put the detector near a black hole and sort of have it register the radiation and look at the spectrum of the radiation, maybe even and so on and so forth. That's not so easy, it turns out, but maybe we can have a sort of an indirect argument. And this is certainly the way it's been presented initially when the theory was formulated. The black hole thermodynamics was by Bekenstein, one of its founders, he was giving arguments that were supposed to underwrite this analogy. These arguments drew heavily on information theory and information theoretic understanding of entropy in order to underwrite what you could call the physical salience of the formal analogy between black hole entropy and entropy in well-known thermodynamic regimes. Now, about 20 years ago, I'm just using Sorkin here, Raphael Sorkin, as one example. Pretty much any physicist, I think, could have said that who works on this, I think. Namely that Hawking radiation is the best known piece of evidence for the association between the horizon area with entropy. It's really sort of the central piece in black hole thermodynamics. Without Hawking radiation, it's not clear that black holes should be considered thermodynamic objects. In fact, physicists didn't really take the analogy between the area of the horizon and an entropy in the thermodynamic sense very seriously until it was established that there is radiation. The thinking behind this being, of course, that classically speaking, a black hole is a perfect absorber. You wouldn't expect that there's any radiation coming off of the black hole. So if you think that, then why would you think that the black hole is a thermodynamic object? So there should be some sort of radiation, there should be some way in which a black hole can equilibrate with other thermodynamic objects and so on and so forth. And Hawking radiation provides that mechanism. So that's why the sense in which it's very central. All right. Okay, so once Hawking put forth his semi-classical argument that there is such a radiation, then all of a sudden this really becomes a very serious matter and firmly establishes black hole thermodynamics. So the association stands between the horizon area with entropy and therefore with really black hole thermodynamics stands and falls with Hawking radiation. However, Hawking radiation is a theoretical conjecture. It's the result or the conclusion of an eminently reasonable, plausible calculation you could do. But it's not something that's been empirically confirmed, empirically directly detected. Of course, if we could do that, that would establish it, and then there would be no, grounds even for radical empiricists, as it were, to doubt the association. Now, the problem is Hawking radiation of at least astrophysical-sized black holes is really not detectable in practice against the backdrop of the cosmic microwave radiation. Why not? Well, the temperature of the Hawking radiation, you would expect for a black hole of just a solar mass, which is a relatively small black hole by astrophysical standards, would be already just a tiny 10 to the minus 8 Kelvin or something of that order, maybe 10 to the minus 7. And for a supermassive black hole that you would expect of the kind that you would find in the center of a galaxy, such as Sagittarius A star, for instance, it's more of the order of 10 to the minus 14 Kelvin. So there's really just no hope that we will detect any of that against the fluctuations of the cosmic microwave background. About 40 years ago, Bill Unruh had the wonderful idea of then move to analog systems, to systems which in the relevant sense would be analog to black holes, that is, they're relevantly similar, physically speaking, as black holes, yet they have the huge advantage of being creatable and controllable in a lab environment, a terrestrial lab. In fact, the physicist Jack Steinhauer, about 5 years ago, has claimed to have observed Hawking radiation in analog systems, including, in his case, it was a Bose-Einstein condensate. as far as I know, that's not been reproduced, but I mean, I leave the details of the exact status, experimental status, to physicists working in analog gravity for that. For today, let's assume that this can be done, has been done, or can be done, or will soon be done, or so, that this is possible to create a Bose-Einstein condensate in your lab, or a hydrodynamic system in your lab where you observe analog Hawking radiation. Now the question is, of course, how exactly does this analogy work? Is it really of the kind that we can learn something about black holes? Do we learn something about Sagittarius A star when we perform some experiments on our Bose-Einstein condensate in a lab of the University of Tel Aviv? And for that, we need to look a bit more closely at the basic idea here, which is that if two systems are known to be similar in some relevant respects, then we can assume that they're also similar in some unknown respects. The idea is that the modeling is similar in both cases. That's why they're analog systems for the Bose-Einstein condensate and for the black hole. And therefore, if we see Hawking radiation in one of them, we would also say that we should expect rationally now to see Hawking radiation in the other case. That's the sort of the unknown respect, the respect of interest, as it were, to us. So the central question is, can analog models confirm not Hawking radiation in those analog systems, but gravitational or astrophysical Hawking radiation? Can we learn anything about black holes from these analog models? Or more generally, can analog models confirm hypotheses regarding inaccessible target systems? Like, Sagittarius A star is not exactly so easily accessible to, certainly not to manipulation of the way we use it in normal experimentation. Okay, now, a few years ago, 5 years ago, three philosophers, Radin Dardashti, Karim Tebo, and Eric Winsberg, have put forth a thesis that yes, in those cases, we can, in fact, obtain confirmation for the hypothesis that there exists astrophysical Hawking radiation. So analog experiments, they say, can yield confirmation. They can give us reason to believe in, or sort of expressing it quantitatively, increase our credence in particular hypotheses about the systems they're supposed to represent. In particular, they say analog gravity can confirm gravitational Hawking radiation. The idea is, I don't have a pointer, but I hope it's clear enough. So we have over there a target system. That's the system of interest. That's what we would like to know something about. We want to learn something about this. It's the black hole, of course. And then on the right-hand side, we have the analog system, some analog gravitational system, which is maybe a Bose-Einstein condensate.
Just press the light.
Okay.
It's not very bright.
Oh, yeah. Here, the Bose-Einstein condensate, or the hydrodynamic system, or whatever your analog system is. And now, in both cases, you model the physical situation. You have a theory of the physical situation. So here you have the semi-classical model of the black hole, of its thermodynamic aspects, which describe the black hole, and where you would find, theoretically, you should have some radiation. Now, here too, you model that physical system, so you have an analog model. Now there are two conditions you have to sort of check, and this is what underwrites what philosophers of science would call the external validity. That is, the validity of applying the results of one system to another system, another kind of system, in some sense, different system. And in order to establish this external validity, is the idea, you need to check two conditions. The first one is that this is what Dardashti et al. Call a syntactic isomorphism. So basically you have to have the same mathematics. You have to have the same model. It doesn't have to be exactly identical model, but it has to be relevantly isomorphic, the same, giving you the same structure. Now, that gives you sort of the mathematical, the formal analogy between the two. But of course, you need a little bit more now. You need some sort of adequacy conditions to be in place in both cases. You need to convince yourself that this is not just a formal analogy, but that these formal representations, the models you have, correctly describe the physics that's going on. If you do that on both sides, you have adequacy conditions on both sides, convincing you that this is the correctly captures the physics, then you could say you have a physical analogy. And the idea, once you've established this, is now that if you observe Hawking radiation in your analog system, then that would confirm the existence of Hawking radiation in the target system, in the system of interest. That's the general sort of setup. And here's Dardashti et al. They actually give a rather complicated argument, which I somewhat simplify here to highlight what I take to be its most salient and most relevant aspects. In particular, they specify that two steps need to be performed in your work in order to establish that analogy. The first one is that for certain purposes and to a certain degree of desired accuracy, the modeling framework MS is adequate for modeling the system S within a certain domain of the conditions DS. So that's in the, that's not the target system, that's the system, the experimental system. You have to convince yourself of the adequacy there. Now in step 2, they say basically the same thing for the target system. For certain purposes and to a certain degree of desired accuracy, the modeling framework MT is adequate for modeling system T, the black hole, the target system, within a certain domain of conditions dt. Now, if successful, these steps would establish the physical salience of the otherwise merely formal analogy. That's the idea. So they're absolutely, ineliminable steps. Otherwise, we're just doing mathematics. Clearly, we want to do physics. Okay. Now, in step 2, therefore, and that's the relevant part here, the authors are assuming that black holes are accurately, or at least sufficiently correctly described, or sufficiently accurately described by the modeling framework from which Hawking radiation is derived. That's part of the setup, part of the assumptions that go into the argument. They write the system of type T, in this case the astrophysical black hole, is the astrophysical black hole. The modeling framework MT is a semi-classical model for gravity in which we have a fixed classical spacetime that features the establishment of an event horizon by a gravitational collapse leading to a black hole and to a quantum scalar field evaluated in the regions of past and future null infinity, which are assumed to be Minkowski. So the semi-classical analysis. The domain of conditions, dt, is limited to the times after the collapse phase of the black hole, the details of which are assumed to be irrelevant. The work in dealing with the Trans-Planckian problem discussed above is sufficient to demonstrate the viability of the modeling framework for some future refinement of ds. So you have to convince yourself that the Trans-Planckian, so-called Trans-Planckian problem is not a problem, it's not going to undermine these adequacy conditions. But the problem is, all of this is theoretical, and there's a sense in which it invites a certain circularity. So you have to assume that the modeling framework you're using to describe the situation in the case of the black hole is correct in order to get to the conclusion that astrophysical black holes emit Hawking radiation. But of course, that's exactly what we would like to know, in a sense, whether the modeling that Hawking used is correct, is physically adequate to capture the situation in the black hole. Now, of course, how do you do that? If you would like to know whether that's correctly done, well, again, one way, the normal way in physics would be, well, let's do an experiment. Let's, ask the government to fund some research. We do the research, we make an experiment, we convince ourselves that, yes, this correctly describes the physics. That's obviously not going to be available here. That's the problem, right? Or, alternatively, we could have a fundamental theory of which we convinced ourselves independently and through other means, which then has as an implication that this is, this sort of way is the correct way of modeling a black hole. Specifically, if we had a quantum theory of gravity, ultraviolet, complete, high energy, quantum gravity, something like that, which we've tested elsewhere, of which we are convinced otherwise, and this theory would imply that black holes have to be, to a good approximation, or can be, to a good approximation described by the way Hawking did it, then that would be another way, of course, of convincing ourselves that this is right, that we can, without problems, assume that step 2 is performed. Okay? Now, the lack of A, as I said, was precisely what motivated analog gravity. So what we should go is, we should then go for option B. We should find a fundamental theory from which the relevant physics is derived in appropriate approximations. And that's exactly where there is a disanalogy between the two cases. In the cases of, in the analog cases, depending on exactly what the analog system is, whether it's a Bose-Einstein condensate or some hydrodynamical system or some other system, we have a fairly good theoretical understanding of these systems, which has been confirmed independently and by a number of different ways. Ultimately, we'll have to do quantum field theory in the right regime for these sort of systems, but that's an extremely well-established, empirically confirmed theoretical framework which is being tested independently. So that's no problem to convince ourselves of step 1, that is the modeling adequacy on the side of the analog system. And the problem is what we don't have that same sort of confidence and empirically justified belief in some fundamental theory that describes a black hole and convinces us that the modeling theory there is accurate. So the grasp on black hole physics is not remotely as firm, of course, as it is on that of the analog systems. Okay. That's the problem. But we need to know whether or not black holes fall into, this is another way of saying the same thing, in the same universality class, the class of systems, understood in a very general sense here, in the class of systems which have the relevantly same physical behavior. That's exactly what we would like to know. So together with Karen and with Niels Linnemann, I've published a paper a year ago where we argued that that's exactly the sort of circularity that you have in the case of analog gravity. So by assuming that black holes are accurately described by the modeling framework from which the derivation of Hawking radiation is a necessary consequence, Dardashti and co-authors already assume the conclusion they're trying to establish, namely that Hawking radiation exists in black holes, more or less. It's in this sense that they're begging the question. We use this term, this English expression of begging the question, and we clearly did not mean to apply it, or to mean to imply, therefore, that it's a fallacy of deductive reasoning, which is sometimes known under that name in logic, like introduction to logic. You assume P, therefore P, what's fallacious about that? Well, you're begging the question. You assume already what you're deductively getting at. We understand we're not in the realm of deduction here. These are inductive arguments, inductive ways of confirmation that we're concerned with, but it's sort of an inductive analog of that. We're nevertheless presupposing a reasonably high confidence in our modeling, the adequacy of our modeling framework, for confirming basically that this is that the black hole is thermodynamic as we believed it to be. Now, of course, an opponent might then argue and say, like, well, first of all, maybe, confirmation was too big a word. You could grant that and say, well, even though maybe it's not confirmation in the way that we would eventually have all our theories confirmed in once we really convince ourselves that these are the established true theories, but we're learning something about black holes. Now, I'm not so sure about the learning. I mean, what does it mean we learn something if it's something different from confirmation then? Okay. Maybe you could say, well, it's not confirmation we add, but it's plausibility we add. We make it plausible that we should expect Hawking radiation in the astrophysical case. But again, I mean, it was already made plausible insofar that the modeling framework Hawking used was plausible that we should expect that. So it's not clear whether we really add something. Okay. Anyway, what we dispute in that paper is that this can really be adding confirmation. Now, Radin, Karim, Eric, and Stefan Hartmann, who's joined their team, have tried to make it more precise by what they mean by confirmation in that context. And they said, we mean by confirmation a Bayesian form of confirmation. A Bayesian form of confirmation is a quantitative form of confirmation where you want to show, or where you want to define confirmation as something like conditionalized, increase of conditionalized credence. So a hypothesis, give the probability or the credence in a hypothesis is larger than, is given the evidence you now have, the additional support, the empirical data, whatever, is bigger than it was before you had that kind of data. That's empirical confirmation for the Bayesian. And that, notice, can be very, very weak. Maybe your credence was just increased from 0.000001 to 0.00002 or something like that. But that would count as confirmation. So in a sense, it's a very weak notion of confirmation. It doesn't take much, right? And you might think, well, that's good, because if it's weak confirmation, it would be more plausible that we get some weak form of confirmation like that. And they make their point drawing a Bayesian network. They say, look, the situation should be considered to be of the following kind. We have here the analog system, which is modeled in the way it's modeled, and we have some node here, which is the probability that we observe something, given that, namely Hawking radiation. Here, on the other hand, is the probability of M, namely that the modeling framework used in the target system is there. That's this node, this variable. And the variables M and A are connected by a joint factor of X, which is sort of the idea that somehow both of these systems fall in the same universality class. So M is modeling framework is empirically adequate description of the physics of the target system. A is the same for the analog system. E is the evidence, that's why it's called E, namely that the radiation in the analog system is observed, and X is something like a universality argument that they have the common same modeling framework. And to notice again, or to point this out, it's really the parent node of M and A here, the X node, which underwrites the universality claim. This has to be there, this connection, for otherwise there's, in the Bayesian network, you would not get any change of the probabilities over here by adjusting probabilities over there. And they prove a theorem. They prove a theorem, namely that assuming a positive probabilistic dependence of each of the three edges in the network, it's the case that the probability of M given E is larger than the probability of M. And that's exactly the Bayesian sort of confirmation. Namely, the probability that the modeling framework is correct in the case of the black hole, given that we've observed now Hawking radiation in the analog system, is larger than the probability of E. Okay. Now, there are three conditions. This is the assuming part here, expressing the probabilistic dependencies, namely that the probability of M given X is larger than the probability of M given not X, which is equivalent to the probability of X given M being larger than the probability of X. That means that's the form of asserting some sort of positive relevance of the universality argument for the target system. Right? Because now your condition lies here on M. So yeah, that's a positive relevance. Okay. Now, obviously the argument of the claim is that this situation correctly captures the situation, and they say, look, this is appropriately modest because we didn't tell you that the links, the X factor, the X node, and the links to M and A are all that strong. Maybe you're really skeptical whether M falls under this universality class X, in which case you can assign a very, very low probability to that link. I mean, on this, positive relevance may be very low in that sense. But what you assume is that it's at least possible that there is such a positive relevance. Otherwise, you wouldn't be allowed to draw the link at all. Now, by connecting variables X and M, therefore, you already presuppose in a probabilistic sense what you would like to establish, namely that black holes fall into that universality class. Now, you could say, as a defender of this Bayesian confirmation, in this case, like, look, all that we need really is just that the probability of M is non-zero. And surely, you might have all sorts of doubts about whether the modeling framework in the black hole case is a good modeling framework or not. Maybe we shouldn't really be all that confident. Maybe you're really impressed by the trans-Planckian problem, or maybe you have some other reasons to think that it's probably not going to really work out. But surely, there should be some sort of non-zero credence in the proposition that this is correctly described there. And also this inequality that M given X should be larger than M given not X seems to be reasonable. So you're being very modest here when you claim that. You don't make any grand claim that this has to be like that, or very likely to be the case or so. Not at all. You just accept the probability, which seems to be, the possibility, which seems to be epistemically eminently reasonable. this is also defended not just by Dardashti et al., but also by Grace Field in a forthcoming paper against us. Now, it may seem that this is a weak assumption, but we think it's not quite as innocent as it may appear, actually, because it does imply, via the theorem you can prove, which is proved in the second paper by Dardashti and collaborators, that you could do a large amount, perhaps, of terrestrial experiments on all sorts of analog systems. You do many tests on Bose-Einstein condensate, hydrodynamic systems, and so on and so forth. You find maybe a whole sort of range of analog systems. You find Hawking radiation in all of them, and all of this, according to that theorem, then should therefore increase your credence that black holes do emit Hawking radiation. Now the point is, you could increase this quite a bit without ever looking at a black hole. You could do just terrestrial experiments. That's the way the mechanics of the Bayesian approach work. But if you're interested in precisely whether black holes are appropriately modeled that way, that is, whether or not there is a connection of positive relevance between X and M, that's exactly what we would like to know. Now, this is an example Niels came up with. I'm sorry this looks very green. In the original, it was just a mild yellow. Think of it that way. So the philosophers among you probably know the debate in the philosophy of mind between dualists and physicalists, or people who are functionalists who think that really their mental states are not sort of a different sort of thing from physical state. They just sort of emerge out of this by maybe perhaps some complicated way. Now, you could say, well, we could now do a similar kind of argument in that case. We could assign to the functionalist or to the monist, the physicalist, some sort of prior probability of 0.75, namely to the claim that any system with a certain functional design, relevantly like a human brain, will in fact have consciousness, belongs to the universality class of consciousness, having mental states of a certain quality, perhaps, something like that. Now, as a dualist, you wouldn't want to say that's 0.75. You think that's way exaggerated. But of course, given that this is a Bayesian sort of framework in which we cast the problem, and which has been accepted by both, the dualist will have to give some sort of low number to that, prior credence of maybe 1%. All right? So the different priors, perfectly natural, and that captures in a way the disagreement between the two. Now, as I said, neither of them is permitted to take either 0 or 1. That's ruled out in the Bayesian confirmation theory. You're not allowed to give absolute certainty of the truth or the falsity of a statement. Now, so the question is then, whether or not some sort of structure which is sufficiently complex, like a human brain, will have consciousness, right? And now we're going to be able to increase our credence in that the population of China, I think, is sometimes, or a complicated system of water pipes and valves, or whatever, you can come up with some sort of analog system, something that's relevantly like a brain, but is not a brain, a human brain. You could then increase your credence in functionalism, say, by observing many humans, studying, whether they really actually have that kind of brain, and you notice, oh yes, they're conscious, the next one is conscious, this one is conscious. You perform many measurements on these analog systems, The target system being some really different but structurally similar system in which you would like to know whether consciousness exists. Okay? Now, but of course, the dualist wants to complain that no matter how many humans you're observing, or maybe sentient animals or something like that, none of that is going to have any bearing whatsoever on whether your water pipe system is going to develop consciousness or not, because it's just not relevantly analogous, right? So they would want to say that we can never learn anything about the target system from that. In a sense, observing humans does not address the research question, which was about the target system, not about humans. And similarly, you could worry that in the case of black holes, you could investigate as many terrestrial systems as you want. That's just in a way not addressing what we want to know, namely whether black holes, the kind of things which sit in the center of the galaxy, are astrophysical, or sorry, thermodynamic objects. Okay. Okay, good. Now, as philosophy goes, yes.
I have a clarification question about the previous argument. Can you please go to that slide? Okay. So I don't understand the third bullet. Now we observe thousands of humans, and each time we raise the probability a bit. So if the research question is that there is a system with a certain functional design, and that is that's how we're delineating this universality class. And now we have a target system we want to learn about, and then we look at accessible systems that we think also belong to that universality class. Wouldn't human just be one type of accessible system that belongs in that universality class? So it doesn't matter if you observe thousands of humans, you're just looking at one type of accessible system, and in order to raise your probability, you would have to look at, a sentient animal that would count as a second type of accessible system, or AI that would count as a third type.
Good. No, you would do both. You would, of course, try to do both, but in the Bayesian dynamics of confirmation, both would actually contribute to increasing the probability. Even though it's true, if you look at just humans, of course, you would come to the point where the added value of observing yet another human is going to be very small. So in order to then make some significant progress, you would have to start to look at cats, or then at bears, or whatever, things like this, and that would then give you another boost in the confirmation. But of course, that presupposes it's kind of given already, how that humans are one type of class. Maybe it's not humans per se which are one type of system. You could then say like, no. But so far I've just looked at female humans. Maybe male humans don't have consciousness. Let's do that. And that's a second kind. And, oh, that gives us new confidence. Yes, males have consciousness too. And then we can see whether, I don't know, green-eyed people and blue-eyed people and all sorts of eyed people have consciousness. And we can convince ourselves that all of these different kinds of people have consciousness. And we've checked, but now we add, again, confidence.
So I still don't understand that, because isn't the parameter by which you're defining the universality class a certain functional design? So then gender, the color of your eyes, wouldn't bear on that parameter.
Yes, yeah, we would assume that all humans are in that universality class, exactly.
Okay, so maybe I can ask you later, but I guess I'm just not understanding why you could arbitrarily subdivide humans and say that each subsystem or subclass of humans would give you a boost in raising your credence based on how you parameterize the functional design that your research question is interested in.
Because you wanted to say that if you look at different kinds of objects or systems in the universality class, that should give you more of a boost in the credence than if you look at just systems of the same kind. What I'm replying is, yes, that may well be so, but it, among other things, will depend on on classifying the systems in the universality class into kinds of systems. I mean, that's, at the end of the day, this is a lot of what's going on here. So what kind of systems fall into the same categories? Are they relevantly the same or not? If you perform the experiment on Bose-Einstein condensates in Jerusalem, is it going to be the same as if you perform the Bose-Einstein condensate experiments in Geneva and things like that? And you know, there's a lot of intuitions which go into classifying these as the same or different, and that's a highly non-trivial matter. And depending on how you do that, it's true that if you move to some different kind of thing, you get another boost of confirmation, but it's still going to be the case that you get some confirmation from you know, testing more systems of in that universality class without ever looking at the system of water pipes, whether that's conscious. Okay. I'm kind of running out of time, so let me try to give you a little bit of a sense of the sort of state of art of that debate, because of course as philosophy goes, Corinne Thébault in particular and Pete Evans have not accepted our argument and have argued against it. Here's what they say. They say that one of their core claims is that an experiment of a manipulable and accessible source system, such as the system in your lab, of a certain type can, in some circumstances, be used to make inductive inferences regarding a target system of a different type. Now that, I take it as completely consistent with what we've said, that in some circumstances this is possible. In particular, when we have good reason to believe that the source of target phenomena in questions are universal, it is possible to make inductive inferences from the existence of the phenomena in the source system to the existence of the phenomena in the target system. Such inferences constitute a new form of intertype. So in some sense, you presuppose that then there are different types of systems, and you make now an inference from one type to another type. That's an intertype uniformity principle that you assume, which play a structurally similar role within inductive inferences to that played by more standard uniformity principles, say across space, that you have uniformity of spatial distributions, whether you do it your experiment in Jerusalem or Geneva, doesn't matter, for instance. You have across time, whether you do it this year or whether you perform the experiment next year or so, you have a uniformity principle underwriting that. Intratype, if you use the same type of system, like your Bose-Einstein condensate, it's going to be this one and that one, but of the same kind, is going to increase that confirmation, etc., etc. So they say, basically, when you do a uniformity inference of intertype to a different type of system, that's nothing systematically new. The relevant question is whether this induction that they call inductive triangulation is problematic in Hume's sense of somehow illicitly assuming a uniformity across space-time, intratype and intertype. Whether it's just like, Hume's problem of induction, which we have when we must presuppose a uniformity across space, across time, for instance, within the same type of systems, whether that also applies when we make an inference to other kinds of systems. Now, I omit some irrelevant detail of their rebuttal, or as I'm tempted to say, attempted rebuttal of our argument. They think that the kind of skepticism we've expressed is of the kind that's unreasonable doubt, like the doubt you could justify by invoking Hume's problem of induction. It's really nothing other than a form of inductive skepticism that, of course, in some sense, we cannot, by a philosophical argument once and forever rule out. We have to live with that. But it's just inductive skepticism of that very uninteresting form that we have here, and therefore, if we want to do science, I mean, that we have to put that aside anyway. Now, to look at a little bit more details, the inductions here are two kinds, from accessible systems to inaccessible systems, from a system in your lab to a system at the center of the galaxy. And you have intra-type, from one Bose-Einstein condensate to another Bose-Einstein condensate, say, an inference, to inter-type inference. That is, from a Bose-Einstein condensate to a black hole. Now, they give us a very interesting example of somewhere where we do, where we can actually get confirmation on an inaccessible system. It's not the case that just because a system is inaccessible, we cannot possibly get confirmation. Consider the case of stellar nucleosynthesis. In main sequence stars, that's a family of stars of which our sun is one, the theory says that there are two principal reaction transformations from hydrogen into helium, the so-called proton-proton chain and the carbon-nitrogen-oxygen cycle. That's the two ways in which helium is produced in the sun or in sun-type stars. Now, both take place deep within the stellar core, not on the surface of the observable surface of photonically, visibly observable part of the sun, with a relative abundance of these two reactions depending on the size of the star. Both processes are unmanipulable, of course. We cannot manipulate the interior of the sun. Both of them are, at least photonically, inaccessible. We can't see these, into the interior of the sun. I should note, however, as they do as well, that doesn't mean it's completely inaccessible to observation. There is, for instance, a neutrino flux from reactions in the interior of the sun that can be observed on Earth. So in that sense, it's only in one form, empirically inaccessible. Now, as they rightly say, the inference from observed phenomena of stellar surfaces and in interstellar space, so, the space from between the sun and Earth, say, as well as from the observed spectra of terrestrial atomic systems, on systems we have access to and directly are manipulable, etc., of atomic systems and nuclear phenomena, the theory of stellar nucleosynthesis is largely confirmed. There's no serious astrophysicist which does not believe that this is basically right. And that strikes me as correct. I wouldn't want to be found as disagreeing with that, of course. Now they say, ha, if you accept that, we got you because this is a well-confirmed theory about an inaccessible system. They think now there is, prima facie, only one fundamental difference between the two forms of inference. That is, in the case of stellar nucleosynthesis and astrophysical Hawking radiation, the two cases of interest here being compared, if one thinks that there is a fundamental difference in kind between intra-type regularity principles and inter-type regularities, as embodied by universality arguments. They find that there's nothing special about the intertype inductive reasoning that bars somehow their inductive inference of the usual form. And they base this on two observations. First of all, they say a lot of intra-type reasoning in science might be interpreted as inter-type reasoning in a given context. That's what I referred to earlier. It's the classification of systems into certain types may be context dependent and may vary in different scientific contexts. But that's not somehow a principal problem for science. So what is intra-type in one case may become inter-type in another sort of context, and that seems to be unproblematic. And they give an example where they think this happens. Moreover, they say there exist examples of scientists using Wilsonian-type universality arguments in physics now, to justify inter-type reasoning of this form in a range of condensed matter contexts. So they say that there are universality class of different types of systems, and we use a sort of a Wilsonian analysis to argue that nevertheless we can, what we've learned on one system now apply on another system, or what we observe in one system can be thought to be, okay, I need to finish up. Anyway, the relevant thing is in this diagram here. So we start from completely harmless, accessible intra-type inferences, which can now be changed to either be inaccessible intra-type or accessible inter-type inferences. But what is of interest here is that it's a combination of both. The black hole seems to be of a different kind than the Bose-Einstein condensates, and at the same time is an inference to an inaccessible type. Now, they think that combining a sort of concatenating these two forms of inference doesn't add anything new, doesn't add any special problem. So if the horizontal and the vertical directions are okay, it seems to them that the diagonal inference should be okay as well. Now, I think that's just not necessarily right, because it's not the case that from one type of inference which is okay and another type of inference you can infer that the combined induction is okay, because we're not doing classical logic here. It's induction. So that may not be valid. Okay. Now, to me it seems that it's precisely the combination of simultaneously inferring from a system which is accessible of one kind to a system of another type that is, moreover, inaccessible, that is problematic in this case. So it's given the inaccessibility of the system, we cannot assume that it's of the relevantly same type, that is the same universality class. Okay. Concluding. Last slide, I promise. Black holes may well be thermodynamic objects. I really hope nobody takes what I've said in the past hour as somehow against that. That's not the point at all. Establishing that they are, however, seems to me far from trivial. And it's an interesting case in which you have theoretical arguments of different kinds which are trying to support that conclusion. They are very suggestive. I don't deny that at all. They're extremely suggestive, very compelling arguments in my view, but they're not conclusive. In an empirical science where ultimately an empirical test is the arbiter of truth, therefore they shouldn't be considered conclusive. And I've argued that trying to say that there is a form of confirmation, of support, of increasing our credence that the theory is true, would require a form of circularity that we cannot address unless we find some other way of accessing black holes. Eventually, nothing can give us further constraints on theorizing with quantum gravity than directly relevant empirical work, such as the observation of black holes or other astrophysical objects. So let's do astrophysics and quantum gravity phenomenology. That, I think, is the take-home message. Thank you very much.
Okay, so questions. Wow. I'm afraid I haven't learned everyone's name yet, but yes, yeah, what's your...
Paul.
Paul, yeah, okay, great. So Paul first. Can the other people keep their hands up and I'll yeah, let me just raise some. Can I ask people to speak up? I moved the microphone a bit further, but please, yeah.
Yeah, so I was, during the talk, I was thinking maybe these analogy experiments or experiences are actually more common than we think they are, because, for example, when we're young learning physics, we learn about Newton mechanics, but its domain of applicability is the solar system and stuff like this. But
You can put them down there.
very young physicist, I was like, oh, I'm sure it works very well actually at small scales and like small particles or at our scale. But so is that a similar type of analogy, or is it a different type? And what I thought of then is, well, why this Newton mechanics analogy seems fine is because we have this type of metaphysical presupposition that everything's made of the same substance, the big and the small. As in with the black hole one and the condensed matter, we don't have really this presupposition that they're made of the same substance.
Okay, so what's the analogy exactly between? So analogy between system of different kind of substance.
Yeah, so the Newton one is the stars. We look at the stars that are moving well, but we think of also small particles will behave in the same way. So is that an analogy, or that would not be an analogy?
So we would think that like maybe sort of a system of terrestrial physics, of like, if we shoot cannonballs at city walls and stuff like that, whether we use the same laws of Newtonian mechanics as we do when we try to understand solar system physics. Now, that's an analogy. That's not a priori obvious that the theory, the way of modeling these very different systems is the same, but it's relevantly different from the case here because we can test individually and directly that the theory is a good theory in both cases.
Yeah, but we also, like, when we're young physicists, we really think, oh, it's going to work for small particles also, Newton mechanics. We have strong confidence.
So something we do not have access to,
Yeah.
Because the particles are too small
Yeah.
for us to observe directly. I mean, if these are empirically inaccessible, yeah, maybe it's going to be a similar problem. You will encounter the challenge of, why would you expect that very different kind of system, which is empirically inaccessible to you, going to be governed by the same physics?
So we have this type of way to say, oh, those are similar type. So if I look at my stars here, I look at my stars there, I can say that these are similar types. So we have this notion of being able to compare similarity.
Right.
So is that also an analogy also?
So then it becomes, the relevant substantive question of what, underwrites the similarity claims or sameness of substance or something like that, which is again like the universality claim here. Do the solar system and the tiny particle system fall under the same substance class, as it were, or not? What grounds do you have for assuming that? What kind of confirmation can you get from observing the solar system and how elementary particles would behave? You would have to be careful in that inference, and it turns out, well, the tiny particles are governed by different physics, so you would have made a serious mistake assuming that. And this was found empirically.
David has a finger on this, so maybe you just
Chris
answer.
just made is actually pointing out again.
Okay.
Okay.
Good. Then Catherine, I have you next.
I was wondering, with this kind of Bayesian confirmation argument, where exactly you would say it goes wrong. So is it just an inappropriate use of Bayesian confirmation, or would you want to say something about the probability you shouldn't have given it's not appropriate to give a credence in the universality claim?
My problem with Bayesian confirmation theory is that it requires you to write down basically the network of the nodes and the connections between them. And Bayesians tend to think that this is a completely harmless and sort of assumption-free way of starting, because the presuppositions are so mild that any reasonable person should agree to, and therefore it's not problematic. And I think that, no, that's not quite right. It is an assumption, a substantive assumption, when you write down how the network works, that there are connections between these nodes or not. That's a substantive assumption. And which, for instance, would rightly be contested by the dualist, the analogy that I was trying to do with the philosophy of mind. Because the dualist would think like, well, no matter how many terrestrial animals and kinds of animals you test, it does not tell me whether, you know, a Martian with a somewhat, you know, similar brain structure, nervous system or so would actually develop consciousness or have consciousness, or a water pipe system or any sort of AI, some artificially built robot or something.
Eugene.
I guess kind of related to Catherine's question, like I want to ask like who's begging the question against who, but I guess we just answered the question. But then the follow-up would be, you know, if we gave up this Bayesian sort of theory of confirmation, at least in this context, what sort of notion of confirmation you might have in mind otherwise?
Mm-hmm.
And yeah, you know, just.
So let me be clear, I'm not in principle against Bayesian confirmation. Bayesian confirmation theory has its pretty well-known weaknesses, limitations, and strengths, I think. The point I'm trying to make here is that it's nevertheless the case that you know, substantive assumptions go into it. Now, I don't think, I mean, I wish I had a confirmation theory available. I would, you know, rush to publication if I had it, I think. I don't, and you know, all known approaches to formulating confirmation theories, unfortunately, we know, suffer from serious problems. So I don't really know how to do that. But it's clear to me that a philosopher of science can even so not give up on confirmation, because it seems to be such a central idea in science. And we do want to say these theories are much better confirmed than those other theories, and so on and so forth. We want to have something like confirmation available when we discuss the attitude of scientists to certain scientific theories. That seems to be absolutely central. And for me, it has to do, and this is maybe an important difference between me and the Dardashti, Thébault, Winsberg, and Hartman group, is that for me, confirmation has something to do with the belief that a theory is true, or at least relevantly captures some objectively existing structures of the world somehow, gets it right, so that there's something, you know, I want to be a realist, a scientific realist about successful scientific theories. So confirmation has to do something with a theory getting the structure of the world right, at least partially, at least in some approximation, etc., with all the usual sort of, you know, conditionals attached. But that's, for me, the idea. They seem to have a much milder conception of what confirmation is. For Richard David, who's also in sort of, you know, connected to them, it's something like the viability of a theory, or something as like the, you know, the tenability of a theory, or some idea like that. But to me, if you're taking scientific realism seriously, I don't really know what that means to think that a theory is viable. You think it's okay, that justifies asking the government for a lot of money to do research on it, or is it something more? I mean, does it have some practical relevance only? In which case, then I think I disagree. I think in science we want more than that. Or does it have something more? But then it's not clear what it is more, other than somehow something like truth, or something similar. Maybe that's just my limitations as a scientific realist. I don't really understand what they're talking about.
Daniel, please. Yeah.
Dominic.
I'm sorry. sorry. Sorry.
Yeah, I really, really enjoyed the talk. I was wondering if there might be a disanalogy between the dualist example you gave and this black hole case, because it seems to me in the philosophy of mind dualism, there isn't the same sort of commitment to law-like structure. So a dualist is going to want to say there's this other thing which isn't governed, potentially isn't within our physicalist picture of the world, which has these other properties, which might not be there in other systems as just a fact of the matter. But in the black holes case, we're going to want to say this is all physical matter, and if I've got an equation, which in this instance I've got the same form of equation in the other, there's no other stuff going on, it's all physical matter. And so, because I'm just being a physicalist, and all laws of nature, basically you don't have the syntactic isomorphism in the philosophy of mind case, but you do in science, not Jewish might be science, but in physicalist science.
Right. Okay. Good. Now that's an interesting point. I admit I haven't thought of it. I sort of tacitly assumed that there would be laws governing the mental states or something like that as well. And you're right, maybe that's a mistaken assumption. And if it is, then you're right, there is a significant disanalogy between the two cases. So for there to be an interesting analogy to the case at hand, there would have to be something like laws of the mental realm, or this other non-physical realm. And the question is whether they're the same laws at base or not. And to make it analogous to the case of, the black hole case and the condensed matter case, whether ultimately they're described, in the same way or not, so part of the same universality class or not. That would be the debate then. So you're right. For there to be an interesting analogy, we would have to make that assumption.
Which seems to be to collapse what it is to be a dualist, right? Because if the dualist is open to there being law-like structure, which is in other physical systems, but not in the mind, there's suddenly not really a dualist about the mind to me. They're a physicalist again.
But, okay, maybe we should talk more, but it's not obvious, not obvious to me that this would be unacceptable to a dualist. I should think more about these things.
So are either of those questions follow-ups, or okay? And then okay. Good. Very good. Then I have Emily next on the list over there.
Yeah. So you said that you agree that experiments can sort of provide plausibility to some extent, but they don't provide confirmation, sometimes very weak confirmation. So I guess I wondered what you take plausibility to be, if not just very weak confirmation.
Good.
Do you
Great.
have sort of distinct conception of plausibility?
Yes. So I would want to make that distinction absolutely, otherwise it wouldn't make sense to have said that. The idea is that plausibility is not like confirmation. Plausibility is more something like what Niels Lindemann in his dissertation has called pursuit worthiness, and others I think have called that as well. So it's sort of something heuristic, not something in the category of truth or thinking whether or not the theory somehow captures the world correctly or not, but more in the context of research heuristics. Should we, do we have a good motivation, a sufficient justification for continuing research along those lines? And that I think, sure, we do. I don't want to contest, analog gravity, including as understood as potentially leading to insights about black hole physics, should be pursued. I don't think that we should just stop it. What I want to insist, though, is that this is different from thinking that somehow what we find in the terrestrial lab systems gives us confirmation in the sense of the realist will want, the kind the realist will want, about black hole physics. For that, we need to study black holes.
That is a finger, right?
Yeah. Would you say that notion of plausibility is similar then to viability? Because you said what you think that actually think of confirmation is viability of a theory. Would you say plausibility is similar to that?
Okay, I don't have a theory of all these different concepts and how they fit together. I do want to make the broad distinction between heuristics and confirmation. And it depends on viability, what you mean by viability. If viability is something of like pursuit worthiness, of heuristic justification to work on a theory or something like that, then sure, that's fine, but that's then in a different category. If viability you mean something more, that the theory gets somehow the world right, then we're talking about confirmation again. And so I would want to make this basic distinction between these two things.
David B.
Yeah, so I wanted to ask about a particular claim you made when you were talking about the Bayesian analysis. The proponent said there's only two assumptions. We need that certain probability is non-zero and that two variables are correlated in a certain way, and we think that's innocent. And then you made an interesting response that if we grant those assumptions, then in principle, if we perform a very, very, very large number of terrestrial experiments, we could become certain that.
Did I say certain?
Yeah, I think you said that, and I wanted to
Decisive, yes.
So it seems to me you could grant that the probability increases, but that there's very fast diminishing returns, and so you go.
Yes, yeah, okay, good. Thank you very much. You paid attention. No, I don't want to say certain in like an uppercase C or anything like that. So you're right. I mean, obviously we shouldn't be thinking of this as sort of asymptotically going to one. That's not necessarily the case at all. As a matter of fact, it may be asymptotically going to a lower value. That depends a bit on the specific mechanics. In the case at hand and the particular assumptions the prior assumptions you make. And if you're interested, you should read their paper because they show that actually there are upper limits less than zero in some cases, and so you don't get certainty. I'm sorry that I misspoke.
Victoria.
I think my question was mainly answered by your Emily, but I was just wondering, do you think there are any other uses of these analog experiments? Like you said plausibility, is there something else like they sharpen our understanding or something that goes beyond confirmation?
So I think that analog gravity is a very interesting research field, and we learn a lot about Bose-Einstein condensates and hydrodynamics. Absolutely. And I think that has intrinsic value. And to sort of see that there are systems with a different sort of material constitution that nevertheless seem to show in some sense the same universal behavior that we wouldn't have found before we thought about the possibility of analog gravity. I think that's a very interesting research finding. And so there's a point in doing all of this. You just have to be careful to think that, oh, yes, now we've convinced ourselves that Sagittarius A star emits Hawking radiation. Well, for that, I would like to have a look at Sagittarius A star. Or, get some other confirmation of fundamental theory of, how I should think about this system in the center of our galaxy.
That is.
Oh, yeah,
that
I
is a
have
finger.
on this one. So how useful do you think these analog experiments would be if say you have a fundamental theory that then implies that it is going to kind of be in this universal class? Are the analogs, how useful are the analog experiments then?
Good.
If it's all going to come out as consequences of a fundamental theory that's well proved anyway?
Yes.
Is it still useful at that point besides kind of the same kind of niceness we had of knowing more about this universal class?
Then I think it would be extremely useful. Because in that case, then, we would be justified in thinking that, in fact, we're learning something about black holes now. Because we know that black holes are correctly modeled in the same analogous way, that there is not just a sort of a syntactic isomorphism, but that in both cases, on the left side as well, we have convinced ourselves that these modeling assumptions are essentially correct, because we now have trust in the fundamental theory. I mean, realist trust for me in the fundamental theory describing this, and convincing ourselves that in the appropriate regime we get exactly this out. And now we can perform experiments on analog systems and definitely learn everything else for which we have justified reason to believe it is in the same universality class, including black holes.
Siska, do you have a finger on that?
Yeah, small question. I'm just wondering, what if we don't find any evidence for Hawking radiation in these analog experiments? Don't we learn anything about black holes in that case?
Yeah, that's a very interesting point. Physicists I've talked to, they're willing to accept an asymmetry here. Namely that they think that, yeah, we are like you, we're somewhat critical that we're really learning something about black holes when we do these analog experiments and find Hawking radiation, that we should really think that this is something we learned about black holes. They're kind of, you know, there's some which are gung-ho, but many are much more careful than what you might get an impression of when you just read the popular science literature on that, or what science journalists say about that. They're much more careful than that. But nevertheless, many of them would accept that if we convince ourselves that there's no Hawking radiation in these analog systems, they would immediately think we have a problem with our description of the black holes. There shouldn't be Hawking radiation. And it's a very interesting asymmetry. And I wonder whether this is really justifiable, that we have such an asymmetric conception. I mean, what it would have, let me put it that way. I'm not sure as far as confirmation is concerned there should be such an asymmetry. But as far as plausibility is concerned, yes, because that I think it would be a blow to plausibility, or you know, pursuit worthiness, because the heuristic reasons for pursuing that have sort of now been broken down.
I guess, well, if you find confirmation, right, then perhaps you can still question whether the universality, like black holes really like belong to the universality class, etc.
Mm-hmm.
But if you don't find Hawking radiation, and given the formal similarities between the derivations, doesn't that already give you some reason to believe that like Hawking, like the formalism that Hawking developed just doesn't apply?
But that requires an additional assumption again, namely to think that the modeling is correct in some relevant sense in the black hole case as well. It may just not be the right sort of modeling. And at least logically speaking, it would be possible that if you were to correctly model the black hole, you would nevertheless still find Hawking radiation. Now I think what's going on is that that's considered somewhat implausible. The reason why we think that black holes might very much be thermodynamical objects is precisely because of that calculation. And if that sort of breaks down, if that's shown to be problematic, then we don't have any confidence that they are, even though logically speaking, of course, they could be. I think that's maybe the right response to this asymmetry, and to show why the asymmetry is rational. I think there were a lot of fingers.
Does Mike still have a thing? Does Mike have a thing? But I have one sort of 2 minutes. Oh, your questions are really good. Okay, good. Then let's just finish on some fingers.
Okay.
Or not? Is this a finger on this one? Or?
Yeah. I have a question because you said a lot about this Bayesian kind of approach, and usually it depends on which are the priors that have been considered.
Well, it depends on what the priors are.
The priors. So what, any comment about that?
Well, I mean, the priors are not allowed to be 1 or 0, and they're going to, in general, differ. Some people might think like, well, I still have a very high credence, initial credence 0.5. Others are going to be more skeptical, more cautious, and assign a lower. But that's the problem of the priors in Bayesian confirmation theory, which is well known, of course. But what the theorem shows that, you know, whatever your initial assignments are, and they may both be perfectly rational, in both cases, upon observing the presence or the existence of Hawking radiation, in the case of the analog systems, both would have to increase their credence in Hawking radiation in the astrophysical case. So that's the way the mechanism is working. That's what the theorem shows.
One more.
Just very short.
Yeah,
sorry.
David W. has been waiting the whole time, and so...
But it's convenient actually because Cisco asked the form of the question I was going to ask, so my follow-up.
Okay.
I mean, isn't this asymmetry actually the kind of thing that just the Bayesian machinery is going to model quite nicely? I mean, let's suppose I'm 80% confident in black hole radiation, but I'm a bit worried about the translation problem, and I'm also 50% confident that black holes are in the same universality class as my Bose-Einstein condensates. Okay, so if I do the Bose-Einstein condensate check, and I find no Hawking radiation, or I find transient Hawking radiation and dries out. So now my credence in Hawking radiation for black holes drops from, where are we, 80% down to 40%. Like it's a big hit to my confidence that we don't get it. If if I confirm it in the Bose-Einstein case, my credence goes up from 80% to 90%. But it doesn't in any way make me more confident that black holes are in the same universality class as the Bose-Einstein condensate.
Yes.
It's just that there was an open possibility that they were in the same universality class, but there wasn't any Hawking radiation that kept that universality class.
Actually, I think you're quite right. So the Bayesian confirmation theory can certainly model this asymmetry. Even though in their case, the posterior probability for astrophysical Hawking radiation is not going to be 0. It's just going to be hugely diminished, presumably more than, you know, from 80 to 40, but not to 0.
Yeah, well, I was just assuming that I was thinking if I have a prior of 50%, the black holes just have nothing to do with Bose-Einstein condensates. That's the extreme version. In that case, then I can say, well, fine, okay. Conditional on Bose-Einstein condensates having nothing to do with black holes. I've got a bunch of other reasons I think there's black hole radiation, and those reasons haven't been affected by the analog result. But I gave a 50% confidence that black holes were in the same universality class as Bose-Einstein condensates. And conditional on that, there's no Hawking radiation. That's where my 80-40 was coming from.
Right. No, I mean, I see that the Bayesian confirmation theory can model, in fact, this asymmetry. I don't see how that would affect the point about drawing out a Bayesian network in the beginning is a substantive assumption would be affected. You could say that it shows that Bayesian confirmation theory gets the scientific situation right, but I'm not sure it does, even though it can model this asymmetry. Okay.
Yeah, I mean, we're a quarter of an hour over, so I think we should probably say thank you.